All right, ladies and gentlemen, we are about to embark upon our lecture for Chapter 9, Lecture number 1. This is a lecture in which we discuss hybridization and the localized electron model. Without any further ado, let's get started. So in our previous unit, we spent a lot of time talking about molecular structure. In particular, we drew a lot of Lewis dot structures. This chapter, we're going to have a look at a new model which we refer to as the localized electron model, which is a model describing bonding within molecules, in which we assume that bonds are localized and form between two atoms which each donate one electron each to form the bond, and it's the overlap of those atomic orbitals which allows for the lowering of the overall potential energy of the system, and therefore the formation of a stable bond in the molecule. We'll have a look here at an example and understand how that we expect the localized electron model would predict bonding to occur within probably the simplest molecule we could possibly choose, which is the diatomic hydrogen molecule, H2. We'll go ahead and start by drawing a quick Lewis dot structure for hydrogen. Obviously, we have one electron each, and that forms a single bond between those two hydrogens. The electron configuration of that hydrogen atom, as you recall from earlier discussions, is simply 1s1. And so we imagine here that if we took two hydrogen atoms, each of which had one electron occupying that 1s orbital, we would see that if we brought those two hydrogen atoms closer together, in a certain region in space, those 1s orbitals would overlap with one another. And the bond really results from the overlap of those orbitals, where the electrons spend time between the two nuclei, and that puts them at a lower potential energy position, as those negatively charged electrons are now close to two positively charged nuclei, both of which they share an attraction to. So in this simplest possible molecule, understanding how bonds would form is a fairly easy proposition. But as the molecules get more complex and we have different atoms with higher energy electrons involved in different orbitals, it becomes more complicated to understand how the actual bonds are going to fit together within our localized electron model. So that's what we'll have a look at next. So here we'll take a step up in complexity and have a look at how we can explain the bonding we observe present in a molecule of methane. Methane is the simplest hydrocarbon whose chemical formula is CH4. And we can real quick here draw a Lewis dot structure for methane. We've drawn this many times before, so we'll have a quick look at that. We've got a central carbon atom and 4 hydrogens around the outside. And let's again have a look at the electron configurations, which is going to give us information about the atomic orbitals which are present in this system and occupied, and how we might see overlap of those atomic orbitals, leading to a meaningful model for our bonding in the methane molecule. So for the carbon atom, our electron configuration is 1s2, 2s2, 2p2, for a total of 6 electrons, 4 of which are in the valence shell there, 2 in the 2s and 2 in the 2p. And for our hydrogen, obviously we've got, as before, a 1s1 electron configuration. Now, if we have a look here and think about our bonding model as suggested by the Lewis dot structure, we're going to come up with a couple of problems as we look at this model. In particular, when we look at a Lewis dot structure here, we have trouble figuring out how we're going to cause an overlap of these orbitals, because for the methane molecule, the carbon only has 2 singly occupied orbitals in that 2p position. And remember, from our localized electron model, we wanted to form overlaps of the atomic orbitals, each of which contain 1 electron from each of the atoms involved in the bond. Which means in this situation, it appears as if we only have the possibility of forming 2 bonds if we're going to be using those 2p orbitals in order to form our overlap and bond these 2 atoms together. And we know methane has 4 carbon to hydrogen bonds, so something seems amiss already. The second problem we observe has to do with our observations of molecular geometry. As we discussed in our discussion of the valence shell electron pair repulsion model, or the VESPER model, during our last unit, We understand that with one central carbon atom and 4 electron domains around the outside of it, we would expect to see tetrahedral arrangement of our molecule there, with bond angle of 109.5 degrees between each of the carbon to hydrogen bonds. And when we actually observe methane and make measurements of the bond angle, that actually is what we observe in the real world as well. So our model, in terms of the VSEPR theory, correlates very well to our observations of the bond angles present. But there's a problem here again if I want to explain how this bonding is happening by overlapping orbitals in a localized electron model. Because in that carbon atom, we only have those p orbital electrons available in order to form those bonds, we know that the angle between the 3 sublevels of a p orbital, the px, py, and pz suborbitals, we know that those angles are 90 degrees. So how am I going to form a molecule with a central carbon atom in which there's a 109.5 degree bond angle between the carbons and hydrogens, but I only have 2 available singly occupied orbitals, which are at 90 degrees, that is perpendicular to one another? It seems like this overlap just isn't going to work. So the atomic orbitals must not, therefore, be our solution to how we can describe in the localized electron model an overlap of orbitals that will result in stable bonding configuration. Furthermore, we also see that all 4 of those bonds in the methane molecule, we find that those are all energetically equivalent bonds. And if I somehow think to myself, well, maybe I can just move some electrons around and use that s orbital as well as the p orbitals in order to form my overlap, if that were the case, then I would end up with differences in terms of the bond energies because an s orbital electron is held more tightly than those p orbital electrons. So it seems like everything about this atomic orbital model isn't going to work for what's going to need to happen when we form an actual molecule here. So on our next slide, we'll take a look at how we can solve this problem with a new model of bonding. So to come up with a solution as to how we're going to explain those problems with our methane molecule's bonding structure, we are going to consider what we refer to as hybridization. We define hybridization as a blending of atomic orbitals to form new energetically equivalent orbitals in order to form the actual bonds. And what we mean by that, if you have a look here at our energy level diagram here, this is essentially a portion of the Aufbau diagram for our carbon atom on the left-hand side right here. Let's just go ahead and fill in the Aufbau diagram with our arrows representing the positions of the electrons in a free carbon atom. So remember, our electron configuration was 1s2, 2s2, 2p2. Following our Aufbau principle, we're going to fill the 2s orbitals before the 2p orbitals, and according to Hund's rule, we fill those 2p orbitals spin up into 2 of the sublevels rather than filling them spin up, spin down within the same sublevel. So this is our electron configuration energy level diagram for a free carbon atom. And as we mentioned again, this isn't going to work for forming the actual molecule of methane. So what we see happening within a hybridization model is that those 2s and 2p orbitals are going to combine together in a sort of blend to form a new orbital, which incorporates both the s orbital and the 3p suborbitals present there to form a total of 4 new energetically equivalent orbitals, which we refer to as sp3 hybridized orbitals. We get that terminology from the 1s and the 3p suborbitals, which we use to form those 4 new energetically equivalent hybridized orbitals. Note that the number of orbitals which we have present here is conserved. That is, we haven't created new numbers of orbitals. We've just changed them in terms of the wave function present here. And also, we would expect to see a change in the shape of those orbitals, somewhere between the spherical nature of an s orbital and the dumbbell-shaped nature of those p orbitals. They're probably going to look a little bit more like p orbitals than they are like s orbitals because we used more of the p orbitals in order to actually form that hybridization for the sp3 hybridized orbitals than we used of the s orbitals. So it's more similar in character to a p orbital, both in terms of orbital shape and in terms of energy level. You see here it's closer to the energy of the 2p orbital electrons than it is to the 2s. But now we have 4 energetically equivalent orbitals, and as it turns out, these sp3 hybridized orbitals exist at an angle of 109.5 degrees between one another. And so by redistributing those electrons into each of those sp3 hybridized suborbitals, we now have 4 singly occupied suborbitals, each of which can be used to form a bond to the hydrogen atom. So we might imagine now in our methane molecule that we would see the 1s orbital from each of those individual hydrogen atoms overlap now with the 4 sp3 hybridized orbitals in order to form a successful bond in each of those cases, giving us the correct geometry and the correct energy equivalent number of orbitals to form the methane molecule. So now that we've had a look at the process of forming hybridized orbitals, let's take a look now at how the actual overlap occurs as these bonds form. There are 2 different ways we could expect to see overlap of orbitals occur, resulting in the formation of a successful bond within a molecule. The first is what we refer to as a sigma bond. A sigma bond forms in the space along the axis between 2 adjacent atoms. So if we go back to our hydrogen molecule model that we started off this lecture with, if I overlap the 2 1s orbitals of those hydrogen atoms, you'll notice that the position where the overlap of the orbitals occurs is directly in the space along the axis between the 2 adjacent atoms. So 2 s orbitals will form a sigma bond. Likewise, when we consider back to our previous discussion on the last slide about hybridized orbitals, if I have the sp3 hybridized orbital from the carbon atom overlapping with, let's say, a s orbital from the hydrogen atom, you'll note there again that the position where the overlap occurs exists directly in the line between the 2 adjacent atoms, that is, along the axis between the 2, which means an s orbital can overlap with an sp3 orbital to form a sigma bond as well. I can imagine another scenario in which I would have 2 adjacent carbon atoms, each of which has sp3 hybridization of the orbitals there. And if that were the case, I could again see an overlap occurring in the axis between the 2 adjacent atoms. So again, all of those would be options for the formation of what we refer to as a sigma bond. And you'll see that notated there with the little lowercase Greek letter sigma. That's in contrast to another type of bond, which we refer to as a pi bond. A pi bond forms in the space above and below the axis rather than directly along the axis between the 2 adjacent atoms. Now, in order to form a pi bond, we have something tricky happening here. Pi bonds, as it turns out, form from the overlap of unhybridized p orbitals. If you can imagine 2 pz orbitals, each of those orbitals on adjacent carbon atoms next to one another, you see if I take those 2 dumbbell-shaped orbitals and bring the carbon atoms close together, that overlap does not occur at the center of the axis there between the 2 adjacent atoms, but instead occurs both above and below that axis, which would give us the overlap of the orbitals necessary for our localized electron model of bonding to occur. But probably not going to be as strong of a bond as we would expect to see from a sigma bond because, on average, those electrons are further away from the nuclei of the 2 adjacent atoms, and therefore they're held a little bit less tightly by each. Now, in order to form a double bond, we are going to need to make use of those pi bonds, because as soon as we form a sigma bond for the first bond between 2 atoms, that would be directly between the 2 atoms along that axis, I can't put a pi bond there as well because that would essentially imply extra overlap of those orbitals, which would be more electron repulsion and increase the potential energy of our molecule to make an unstable configuration. So generally, when we see a double bond forming, the first bond of the double bond forms as a sigma bond between something like, say, hybridized sp2 orbitals. And then the next bond, the double bond, will form from an overlap of either the py or pz orbitals of the adjacent atoms to form a double bond. So again, sigma bonds along the axis between the two adjacent atoms, pi bonds above and below the axis between the two adjacent atoms. Pi bonds must occur between p orbitals. Sigma bonds have a little bit more flexibility either between s orbitals, spx hybridized orbitals, or some combination thereof. So now that we've seen some of the ways that these orbitals can overlap, on our next slide, we're going to go ahead and have a look at understanding how to determine what sort of overlap is occurring. That is, to determine what sort of hybridization we expect to see within our molecular systems. So what we've got here on this slide is a quick checklist for how to determine the hybridization that's occurring within a molecular species. Steps are fairly straightforward. They tend to cause people a little bit of difficulty at first go, but by the time you've done this a few times, you're going to become much more adept at going through the process rather quickly, and you'll notice that there's some shortcuts along the way to determine hybridization as well that we'll discuss later on. So we're going to start off and we're going to draw a Lewis dot structure for a molecule and go ahead and describe the geometry around each central atom. Now, this obviously makes sense because in order to actually describe the bonding within a system, we need to know how many bonds we're forming, and a Lewis dot structure is a great way to start. Once we've gone through and drawn our Lewis dot structure, the next thing we're going to do is to determine the number of effective electron domains that exist around the central atom. Remember, an electron domain is simply a region in space where we find electrons. That can be occupied by a lone pair of electrons, even by a single electron. It can be occupied by a bonded pair of electrons. It can be occupied by a double bond or a triple bonded set of electrons as well. Each of those just counts as one place in space where we find electrons. That is one domain. So we'll find the number of effective electron domains around that central atom. Once we have gone through and determined the number of electron domains, we're then going to determine the number of atomic orbitals that will be needed to form the desired number of energy equivalent binding orbitals. And when we do that, we're really checking to see that we're not putting some electrons at a way higher potential energy level than others. So if we can imagine that we've got, say, 3 sigma bonds in our system, in order to make those 3 sigma bonds, we need to have those 3 sigma bonds be using energy equivalent electrons. So we're going to need to therefore count up the number of orbitals to make those number of sigma bonds, which would be 3, and we're going to use therefore 1 of the s and 2 of the p orbitals to make that hybridization. So with that set of rules here, let's go ahead. This will make more sense if we see it in an example. So on our next slide, we're going to go ahead and apply these rules to show the bonding structure present in a hydrocarbon molecule we refer to as ethene. So let's go ahead and take a look at our example. The ethene molecule's chemical formula is C2H4. We'll go ahead and follow along our rules for determining hybridization. The very first step, as we discussed, was to draw a valid Lewis dot structure. So I'm going to go ahead and make my C2H4 molecule. We've got carbons bonded to one another with 4 hydrogens around the outside. Counting up our electrons available to make our bonds, we've got 2 carbons, each of which have 4 valence electrons for a total of 8 available. And then the 4 hydrogens each bring 1 along, which brings us up to a total of 12 electrons to distribute. We can go ahead and make our single bonds between the atoms in order to make our skeletal structure. So we've got 1, 2, 3, 4, and 5 single bonds there, which uses up 10 of our 12 electrons. And we find ourselves here in a situation where there's not enough electrons to go around. We notice that we need 4 more electrons to complete our octet rule for each of those carbons, but we only have 2 available, which means, as we've discussed before, form a double bond. So let's go ahead and throw a double bond between those 2 carbon atoms. So we now have our Lewis dot structure. And the geometry of each of those carbon atoms with 3 effective electron domains around each one. You see there we've got 2 singly bonded electron pairs and 1 double bond, but remember the double bond just counts as 1 domain, that is 1 region in space where we find the electrons. With 3 effective electron domains, no lone pairs, that would give us trigonal planar geometry around each of those carbon atoms. So we've got our trigonal planar geometry, and we now need to understand here how we can go ahead and form bonds that will give us the correct number of energy equivalent orbitals required to make this molecule work. So ignore the carbon on the right for the time being. Let's just look at the carbon on the left. That carbon on the left has 3 sigma bonds that are going to be forming here. That is, we've got the 2 hydrogen atoms, each of which are singly bonded to the carbon, and our first bond is always going to be a sigma bond. So we know we're going to form a sigma bond overlapping along the axis between those atoms there. And also, the first bond of the double bond between the 2 carbon atoms is going to be a bond which is going to be along the axis between the 2 atoms, which means we need 3 sigma bonds to be forming here. And to make 3 sigma bonds, when I look at my energy level diagram here for the carbon, I've got a problem again. That is, carbon's electron configuration of 1s2, 2s2, 2p2, as we discussed before, isn't going to work because I've got only 2 electrons in that 2p orbital, and those 2 electrons in the 2p orbital are at 90-degree angles to one another, perpendicular, not the trigonal planar geometry I'm going to need with 120-degree angles between the orbitals. And additionally, I'm going to be making 3 energy equivalent orbitals with which to make my 3 sigma bonds, but I only have 2 singly occupied 2p suborbitals which are currently available in order to make those bonds. So my solution then would be to make a hybridization here. I'm going to blend together the 2s orbital and 2 of the 2p orbitals there to form a total of 3 energetically equivalent, now sp2 hybridized orbitals. And again, we give them that name sp2 because it took 1 of the s orbitals and 2 of the p orbitals to make those 3 hybridized orbitals. So with our 3 sp2 hybridized orbitals right there, I can now make my 3 sigma bonds overlapping to the 2 hydrogens and then the first bond of the double bond for the carbon. I can do the same thing with my carbon on the other side as well. And you'll note here that as I did that, something kind of cool has happened. I've used up 3 of the 4 valence electrons the carbon had available to form bonds, and the one that I didn't use up is currently hanging out, occupying that 2p orbital that didn't get used to make the hybridized orbitals. So now, to make the double bond between our carbon atoms, I could line up those 2p orbitals of each of the 2 carbon atoms that have not been used up and overlap them above and below the plane between the carbons to form a pi bond for the second bond out of the double bonding set of bonds there. So that would imply, therefore, the hybridization we see for each of those carbon atoms would be sp2 hybridization occurring present in our molecule of ethene C2H4. So now that we've done ethene, let's go ahead and try one more here, which is the ethyne molecule. Ethyne is an alkyne molecule, which is a hydrocarbon which involves a triple bond. This formula for ethyne is C2H2. And we'll follow the same procedure that we did last time to determine the hybridization within the ethyne molecule, starting off by drawing our Lewis dot structure. We got 2 carbons again for a total of 8 valence electrons, 2 hydrogens for 2 more, which gives us 10 total. And we can go ahead and set up our skeletal structure here. Carbons bonded to one another, each of them also bonded individually to one of the hydrogens. And skeletal structure there, 1, 2, 3 bonds that we just used up to make our skeletal structure work. And as we do that, we used up 6 of our 10 electrons, leaving us with 4 more. But we notice here that each of the carbons still needs 4 more electrons in order to form a complete octet, which means I need 8 electrons to fulfill the octet rule, I only have 4 available. So we are now in a situation where we need more bonds. And in this case, we can solve our problem with 2 more bonds, that is making a triple bond between the 2 carbons to complete our Lewis dot structure. And with our Lewis dot structure drawn, we can now have a look at the geometry. Looking at each of those carbons, you'll notice that each of the carbons has 2 occupied domains, one occupied by a single bond between the carbon and the hydrogen, and one occupied by that triple bond between the 2 carbons. Remember, each domain counts as only one region in space where there are electrons, so we've got 2 domains around each of those carbons. And with those 2 domains, that tells me, therefore, that I'm going to see 2 sigma bonds forming for each of those carbon atoms, one to the hydrogen, and then the first bond of the triple bond between the 2 carbons. So if I need 2 sigma bonds, I'm going to need to have 2 energy equivalent orbitals to use to make those bonds happen. And that's going to be a problem again because, as we discussed before, I only have those 2 p orbitals, which are at 90-degree angles to one another, and I know that this needs to have a 180-degree angle in order to make that linear geometry work. So it's hybridization time again. We're going to go ahead and now use the 2s orbital and only one of those 2p orbitals to hybridize and make now an sp set of hybridized orbitals. Again, sp from the 1s orbital that we used and the 1p orbital that we used. And that now gives me 2 energetically equivalent electrons that I can then use to overlap to form my 2 sigma bonds. Now that leaves me with 2 2p orbitals left over as well, and those 2 2p orbitals will be occupied individually by the remaining 2 valence electrons in that carbon atom. And that works out really well because now I can form not just 1 pi bond, but 2 pi bonds along the 2 different p orbital axes there. That is, the py and pz orbitals can overlap with one another above and below the plane, and then at a 90-degree angle again above and below the plane again between the 2 adjacent carbon atoms. And that situation now gives me the solution to my problem. Each of those carbon atoms, therefore, exhibits sp hybridization to form those sigma bonds, and that would mean then we have the available 2p orbitals left over we needed to form the pi bonds to form our triple bond as well. So everything checks out the way we expect it to from our Lewis dot structure and observed geometry. So having now gone through a couple of those examples right here, I'm going to kind of give you a little shortcut to help you save time, hopefully for your AP test, should you be asked about hybridization of different molecules. Anytime where you have a central atom that has 2 electron domains around that central atom, the geometry of the structure is going to end up as linear geometry. And with 2 electron domains, that means we're forming at a minimum 2 sigma bonds, which means the hybridization of that system must therefore be sp. So linear geometry gets sp hybridization. 2 domains again is sp hybridization. If we have 3 domains around the central atom, that would imply, at least at a bare minimum, 3 energetically equivalent sigma bonds being formed, which means that we would expect to see trigonal planar geometry for this molecule. And to make those 3 energetically equivalent orbitals for forming bonds there, we would need to therefore use 1 of the s and 2 of the p orbitals for what's referred to as sp2 hybridization. And then very, very commonly, a lot of times, anytime we see a saturated hydrocarbon without any double bonds, this is going to be the geometry that gives us tetrahedral geometry with 4 electron domains around the central atom. All of those hydrocarbon chains like octane or methane, ethane, butane, propane, all those extra ones, all exhibit tetrahedral geometry. And to make those 4 energetically equivalent domains that would give us tetrahedral geometry, we would need to use the s orbital as well as all 3 of the p orbitals in order to form sp3 hybridization to get those 109.5 degree angles we desire between the orbitals for our tetrahedral arrangements. So quick and easy. Another way of looking at it is for hydrocarbons, they ask about all the time. Anytime you've got single bonds between all of your carbons, that's going to be sp3 hybridized. Easy as that. Anytime you have a double bond present between a carbon and another species there, but everything else is single bonds, then you end up with sp2 hybridization. And should you find yourselves in a scenario where you have a triple bond or you have two double bonds around a carbon, in that instance, you would end up with sp hybridization as kind of shortcuts. You don't have to go through and derive it each time.